So after on-device training, now we have another discussion. It's a pre-recorded one session from Microsoft. Rama is going to talk about ONNX Script.
Of ONNX Script, which enables you to author ONNX in Python. Let me start with this short example. This is a definition of the well-known activation function Gelu in terms of other primitive ops in ONNX. Given this Python function definition, the translator produces this ONNX representation, which is a function, ONNX function. As you can see, the Pythonic definition is more compact than the resulting graph, which has around 10 nodes. What you see here is an ONNX function known as a function proto, not an ONNX model. In ONNX Script, Python functions can be used to define ONNX models as well as ONNX functions. Here is a simple example of an ONNX model defined as a Python function. One of the key differences between a model and a function is that a model requires type annotations for its inputs and outputs, specifying their type and shape. Given this Python function definition, the ONNX Script translator will produce this model. As you can see, this model calls the ONNX function Gelu defined in the previous slide. ONNX Script is based on a static translator that translates Python AST into an ONNX model or function. One of the benefits of this static translation approach is that it can handle control flow constructs like if then else and loops and map them into corresponding control flow constructs in ONNX. This example shows the use of an if then else statement used to define dropout as an ONNX function. One of the key distinguishing features of ONNX Script is that it also supports direct execution of the code, not just translation. This direct execution is very convenient for testing and debugging. As this slide here shows, we can use standard debuggers to step through the definition of an ONNX function. Currently, the execution framework uses ONNX runtime as a backend implementation of ONNX primitive ops. However, we can plug in other backends as well, and we plan to integrate ONNX reference implementation here as well. ONNX has support for higher order ops like scan and sequence map, for example. ONNX Script provides a natural Pythonic way to use such ops. Specifically, we can use nested Python functions, as shown in the example here, to represent graph valued attributes. In this case, we have a nested function called sum, which is converted into a graph valued attribute that is specified as an attribute parameter in the call to scan. The translator will take care of converting the Python function into an ONNX graph for use in this op. Let me now take a step back and describe the motivation for ONNX Script. Functions are a key extensibility mechanism in ONNX. They let us strike a balance. They allow us to expose a richer operator API to model developers. At the same time, it allows us to keep the core operator surface area that must be supported by different backends small. At the same time, this also allows backends to develop and use optimized kernels for these composite ops on demand. This gives backend implementers a degree of flexibility. The goal of ONNX Script is to enable easy development of function ops. These function ops can be function ops added to the ONNX standard, But ONNX also supports the notion of custom ops as well as the notion of custom function ops, which are model local functions contained in a model proto. Going a step further, we can also imagine creating a library of custom ops. And this can be an easy way to simplify the development of an ONNX exporter from a framework. In particular, we have an ongoing effort to define torchlib as a library of ONNX functions, and we plan to use this as the basis for PyTorch's ONNX exporter sometime soon. As described in the previous slide, ONNX Script can help simplify the development of ONNX exporters, but it can also let you experiment with ONNX. It allows you to create ONNX test cases. It allows you to debug ONNX backends and our ONNX models. Let me finish with a quick summary of some other features in ONNX Script. Constant letters are allowed and are automatically translated into ONNX constants. We also support automatic casts of constants, allowing us to write polymorphic code like x+1 that works for all types of x. Operator symbols like plus and times are allowed, as is indexing and slicing notation. Nested expressions are supported. As we have seen, control flow as well as the use of nested functions to represent graph attributes is allowed. Types and shape annotations are supported. Finally, we support offsets, which are mapped to classes with ops, their types, and documentation automatically generated from the ONNX specification for standard offsets. So we welcome you to try out ONNX Script. Thank you.
I believe Rama is online, so if there's any questions, he could probably unmute and answer. Any questions on the bridge, Venki?
There was one question. Just read out the question. The question is, how do you deal with side effects, that is like caching when using AST?
Okay, the question was, how do you deal with side effects like caching when using the AST? So Rama, could you unmute and answer the question?
Yes, I'm unmuted. Can you hear me?
Yeah, we can hear you.
I'm not sure I understand the question about ASTs. I mean, in the Python code itself, I mean, we rely on the ONNX representation approach. That there are no side effects except that, of course, you are allowed to assign to the same variable multiple times, but the translator will take care of automatically converting it into a SSA renamed version. So it does handle side effects at that level. But I guess with regards to ASTs, I'm not sure what kind of other side effects they're talking about. But yeah, side effects in the sense of multiple assignments to the same variable is supported and handled by the translator. But not deeper, say heap-based, pointer-based representation. There is no way to encode that in ONNX. Yeah.
Right. Any more questions? Anyone?
All right. Next